Hello, welcome back. In the last video, we covered random forest, which is a backend method uh, of doing the trees for regression, basically. Now we are into the boosting methods. So first, we will be going through the gradient boosting gradient boost trees, and quickly look at the uh, steps what we will take to basically solve the problem for regression, and then we will jump into the coding part of it. So basically, in gradient boosting, we build trees sequentially, which start with a mean value prediction for all the training samples. I'll go into these superficially into these each of these steps. But I'll also link the a better resource where you can find a more detailed explanation of the mathematics involved behind it. So because my focus is to implement them in code, I'm not going into them theoretically much. So after initial mean value prediction for each, we fit trees to predict the pseudo residuals. Residuals are calculated as a difference between the observed and the predicted value for any sample in the training set. Then we scale the outcome of each such tree learned here by a learning rate, and then update the prediction with new trees residual prediction. So once we have updated the prediction, we go on, we repeat these steps. Then we fit another tree on the new residual, which is calculated with the updated prediction. And then once we have a fitted tree, we scale the output, we scale the outcome of each tree by learning rate, and then we update the prediction. And this loop goes on for a set number of trees. So what we need is for gradient boost trees is a data xi by I, uh, then also a differentiable loss function. For regression purposes, this is the data set that we started with, building our initial decision tree and then random forest. So we'll continue with the same data set. And loss function for regression that we'll be using is 1/2 of original minus predicted, which is the residual, and square. So basically, this looks very much similar to the residuals that you see in the linear regression, but here we have scaled it by half. If you go into the in-depth mathematics calculations of it, um, you'll see that by 1/2 is done. Otherwise, it doesn't uh, change any results if you use this 1/2 or even not. Uh, the residuals that we are calculated here are called pseudo residuals because we are not using the exactly same formula that is used in linear regression, which is actual residuals we are referring to. This method refers to. Then we find the derivative of this loss function with respect to the predicted values, and it comes out to be minus of negative of original minus predicted, and this is nothing but the loss function derivative that we'll be optimizing for. And fxi here is nothing but the predicted values from trees and the initial combination of initial prediction and all the trees that we keep on building sequentially. So step one, what it does is we have to find a constant initial value that minimizes the sum of squared residuals. This basically is a single sample residual squared. So we need to sum it across all the samples in our trained data set. And for all that sum of squared residuals, we need to find initial value, constant value that minimizes this initial sum of squared residuals. So which means that we need to find the derivative with respect to predicted and find the value where it goes to zero. Solving the above, we get a constant prediction, which is average of all target values. Therefore, that's why initially I said that it will be the mean of all the target values. Then This f or this would be here f of 0x, f of x of 0 is average of all target values. This in the step 1. Step 2, we'll start building the trees, M trees. Let's say M can be, capital M can be 100. For each tree, initially what we'll do is we'll calculate the residuals. Residuals is nothing but the prediction that happened in the last step, and we subtract it from the observed value for that particular sample, which is here. This is called a gradient in the gradient boost trees, basically. So then we initialize a tree, we fit the tree to the residuals found above, and once we have found the fit the tree, we update the predicted values. So initially in the step 1, the predicted value was just the mean of all the target variables, all the target values. But once we have fit a tree, we update that prediction with this update predicted residuals by this tree. So we scale the predicted residual with the learning rate and add it to the initial prediction. Then once we have the updated prediction, we go start calculating residuals for the next step. Here predicted value will change, and then we initialize another tree. That will be the second tree, fit it on the updated residuals calculated here, and then update the predictions again. So we keep on doing these for a set number of trees that we want to build. So this is basically a overview of gradient boost trees. Um, uh, I think if you want to go deeper into the mathematics to understand more, you can go to the gradient boost trees playlist by StratQuest channel on the YouTube by Josh Starmer, and those are very nice. And even I took help of those to understand it in detail. Now let's jump into the code. All right. So here I have okay, yeah. So I have defined a class skeleton for gradient boost trees. So let's initialize it. So what all things do we need is max depth self dot number of estimators self dot um, will basically need max min samples split self dot trees will initialize this self dot learning rate self dot we have got learning rate, we have got trees share bandwidth. We'll also need an initial value, we'll call this init value. Okay, so or let's say for now I'm just removing this because we have this by default initialize in the decision tree class, so I'm not taking this. Learning rate, yeah, just these three. And estimators, let's say we'll take to start with S10. Max depth, we start with an initial value of 5. Learning rate 1e minus 3 is what we start with. So we don't have to take any initial value initialized here. So when we are now, let's start the fit method. We take in inputs and targets. First of all, what we do is we calculate self dot init value. If you remember from the slides, initial value is nothing but mean of all the values in y. Therefore, we form a predicted variable which is nothing but np dot full life, which is of the shape y, and fill with self dot init value, and we make the d type as np dot float 64. We make them all float. Now we have our predictions for underscore n in self dot. We start our iterations for building n estimated trees. For each tree, first we need to calculate residuals, which is y minus y underscore pred. Once we have our residuals, we'll define a tree is equal to decision tree max depth equals to self dot max depth. And what other parameters do we take in for this tree? Min samples, max features, none. We leave it as none. We are using all the features at every stage to split. This min samples is split. I'm not taking it in as initialized value in the gradient boost tree, so this much is sufficient. We can initialize a tree here. Now we'll fit the tree with x and residuals. Now, once we have fitted the residuals, we need to update our predicted values with scaled with learning rate and the tree dot predict of x. So we take the predictions from the fitted tree on all the training samples. We scale them with learning rate and we update the prediction, add it to the predicted values, which were initially just a mean value average. And then we keep on updating the predicted residuals. Keep adding predicted residuals scaled by learning rate. Once we have this, I think once we have this, we can just go ahead and update self dot trees dot append tree, and then we continue on the loop. In the next loop, again, we'll calculate new residuals with y and y pred. Y pred is updated here, so the residuals will get updated. The residual idea is that the residuals will keep getting smaller and smaller. We initialize a new tree, fit it to the new residuals, again update the predictions, and store that tree. Yeah, so I think that's enough. That's um, good enough point to start the fit. That's sufficient. We are not adding any bells and whistles like early stopping or regularization, etc., things here. There are multiple optimization ways of optimizing this algorithm, but I'm not getting into those right now. So for predict, we need input as an x. y pred equals to np dot full like x dot shape 0, then full value with cell dot init value d type equals to np dot float 64. Now, once we have initialized our predictions for each of the test sample coming into the predict function, we'll iterate through all the trees in self dot trees. We'll take let's say we can directly, we don't need to do anything here. We can just say ypred plus equals self dot learning rate into tree dot predict of x. So this method is defined, is coming from the predict method in the decision tree class. It will predict a value for each of the samples in X. And once we have this, we can just return y underscore pred. So yeah, basically that's a gradient boost tree method. Sorry, class we have defined. Let's run this quickly. We'll quickly do a check. We'll initialize a gradient boost model equals to gradient boost trees and estimators. Let's say we are doing 10. Max depth, let us keep it as okay, let me define something here. 5. Learning rate is equal to 1 e minus 2. So we'll start with a higher learning rate because we are not, I'm not going to use much data right now. Fit X train, I'm just taking 1000 samples. 1000 samples. Let's see if it fits. And if it fits, I'll just keep on and just take in the same predictions for this and just the same method and print the results from this model. Okay, non-broadcastable output operand which it I think let me so if we do it this way and then train it. Okay, yeah, looks good. So let's say I'm doing it an estimate is for 200. What happens right now? It can take a few seconds. So right now, if we see the predictions are pretty uh, off from the target values right now from the y test. So I'm trying to train a slightly bigger model with 200 estimators to see if we can somehow reach to that point closer to this. See. Okay, so I quickly trained this, fitted this model with 200 estimators, maximum depth 5, and learning rate 1e minus 2 for just 1,000 samples in the trained data. And from last result, it was somewhere around 70. We are able to reach a bit closer to our target value. So basically, the point is if you train on the full data and you will have to do experiments on all these hyperparameters they will lead you to predicted values quite close to these in the test. Now, there are a few things that are missing in our classes. Evaluations, validation score. So basically, we can do early stopping implementation into this by using validation set and printing the MSEs at each validation at step, and also evaluating the test scores like RMSLE, which is applicable for this data set. But I'll get back to implementing those in the next video. I'll put an update to this where we'll implement all those uh, small optimizations on this naive algorithm right now. So we'll do some kind of regularization if possible. We'll do random selection of the rows for training the data so that every tree doesn't get the entire X and Y, and we'll do some early stopping implementation as well. But yeah, for now, this is the naive implementation of the gradient boost trees. Thank you. See you in the next one.